So, hello everyone again. This is lecture 4 part 3 of ray optics and optical instruments. Let us move on with the further discussions on optical instruments only. So, I am Sameer Lavankar. Let us begin our discussion. So, in the previous lecture of this part only we started with the microscope. So, for the last conclusion of the last part we got that the image formed at infinity is often considered most suitable for viewing by the relaxed eyes. Fine. Let us move on with today's discussion now. So, first of all the magnification m, we will try to find out the linear magnification value. So, the linear magnification m for the image formed at the near point capital D, this is the near point capital D, by a simple microscope can be obtained by using the relation. So, now what we are doing is we are just finding out the actual relation here. So, it will be equal to nothing but m, which will be equal to V by U. Now, in the place of u we just wrote it that 1 by u is equal to nothing but 1 by v minus 1 by f. Therefore, we will write it as 1 v multiplied by 1 by u hence we can just multiply v on both sides, we get this equal to 1 minus v by f. So, this is the magnification of the microscope. Now, according to our sign conventions, v is negative, n is equal to n is equal in magnitude to capital D. What is capital D? Capital D is at near point D at which the image is formed. Thus, the magnification is nothing but equal to magnification is equal to, now just we are using simple sign conventions here, 1 plus D by f. So, this is your magnification. You just need to remember this formula for your microscope part, that is magnification is nothing but m is equal to 1 plus capital D by f. What is capital D? Capital D is nothing but the image formed at the near point capital D. Fine. So, since D is about 25 centimeters, to have a magnification of 6, one needs a convex lens of focal length f is equal to plus 5 centimeters. So, what is this saying? So, as we know that magnification is m, which is equal to 1 plus, let me write it clearly. So, magnification is equal to 1 plus capital D by f. Magnification is nothing but equal to 6, which is equal to 1 plus what is capital D? Capital D is 5 centimeters for you. Sorry, capital D has to be calculated, I guess. As a let us suppose we need to find out the magnification if the image formed is at 25 centimeters and the focal length is 5. So, just 5 gets cancelled and hence you will find out 1 plus 5 which is equal to 6. So, for focal length is equal to 25 centimeters, focal length is equal to 5 centimeters, you can find out the magnification is equal to 6. Okay. Note that m is equal to h dash by h, where h is the size of the object and h dash is the size of the image. So, this thing can also be applied in this form in sequence here also. So, this is also the ratio of the angle subtended by the image to that subtended by the object if placed at capital D for complete viewing. Note that this is not the actual angle subtended by an object at the eye, which is h by u. So, h by u is different and h dash by capital D is different. So, you just need to understand what is h different between h by f and h by u. Sorry, not h by v only here. It will be what is different between h by u and h by f. So, this is nothing but simple mathematical formulation which we know that what is the definition of magnification. So, magnification is nothing but the ratio of angles subtended by the image to that subtended by the object. Fine. So, finally, the conclusion of this slide is that we should know the value of the magnification, and that value of magnification is nothing but equal to 1 plus capital D by f. What is capital D here? Capital D is nothing but the image formed by the near point capital D. What is f? F is the focal point of the focal length of the convex lens. Fine. So, let us move on to the next part now. So, now what a single lens simple magnifier achieves is that it allows the object to be brought closer to the eye than capital D, quite evident. We will now find out the magnification when the image is at infinity. So, for the previous portion what we did is that we found out the value when the image was at some point that is focused on the near point. Now, we will try to find out what will happen if the image is at infinity. So, in this case we will have to obtain the angular magnification, because actual linear magnification is not possible to obtain first of all in the starting portions. So, suppose the object is at height h, has a height h, fine. So, object is the viewable only. So, it has a height h. The maximum angle it can subtend and be clearly visible is when it is at the near point, it is at capital distance d. So, quite evident before that it is not visible. So, it can be visible at the constant distance capital D here. Therefore, the maximum angle at which it can subtend and be clearly visible without a lens, they are saying clearly it is without a lens, is when it has at the near point at the distance capital D here. So, basically it is viewed at some location this. Fine. So, again, so simple mathematical definition of what is magnification. Magnification is nothing but the angle subtended. Therefore, the angle subtended is nothing but tan theta naught, which is equal to small h by capital D. Now, simple assumptions of ray optics that tan theta is approximately equal to sin theta is approximately equal to theta. Therefore, we can write tan theta naught is nothing but equal to h by capital D, which is approximately equal to theta naught. Now, we use the angle subtended at the eye by the image when the object is at u. So, now this is the third portion here. So, this was the magnification when the object was at infinity. Now, we are using the to find out the value of angle subtended when the image is at the object distance u. Okay. So, from the relation we know that h dash by h is equal to m, which is equal to v by u. So, this is again simple mathematical formulation which we also derived when I was explaining on the reflection part. Okay. So, next is that we have the angle subtended by the image, that is tan theta I. So, what is tan theta I? Tan theta I is nothing but h dash that is image height upon minus v. What is minus v? Minus v is the distance, that is equal to h by minus v into v by u. Hence, we can find out this is equal to nothing but h by minus u. So, that v gets cancelled and this will be equal to h by minus u. This h by minus u can be approximated equal to theta. Why? Because we know that tan theta I is approximately equal to sin theta is approximately equal to theta. Fine. So, this thing, so basically, this is the conclusion of this portion. So, just before going to the last portion, okay, let me end it here and then I will try to conclude everything again. I will try to revise everything again. So, basically there are three parts here. First of all, let me complete this portion. So, the angle subtended by the object when it is at u is equal to minus f. So, basically the angle which is subtended is u is equal to minus f, and hence from this relation here, that is theta approximately equal to h by minus u, which is equal to, as we know that this is h by minus u. So, we can write h by minus u is equal to h by f. Therefore, magnification theta I is nothing but equal to h by f. Fine, which is as is clear in C also. So, as you can see that the magnification which is happening here is nothing but h by f. Okay. Whenever you are calculating the magnification using the angle, that is tan theta and all, then that magnification is called as angular magnification. If you use the simple concept which we use for the near point, then you can find out that it is called as linear magnification. Okay. So, angular magnification, therefore, m is equal to theta I upon theta naught, which is equal to capital D by f. This is one less than the magnification when the image is at near point. So, as you can see quite clearly. So, what you can understand, that is for the first portion, when we need to calculate when the image was formed at the near point, then this m is nothing but equal to 1 plus d by f. Now, subtract 1 from this, then you can get m is equal to d by f. What is this magnification? This magnification will be same as this portion here, that is when the magnification is obtained when the object is at u. Okay. So, this is one less than the magnification when the image is at a near point, but the viewing is more comfortable and the difference in magnification is usually small. So, just basically if let us suppose the magnification 8 is obtained and 8 and 7 which will not have much more difference in the actual magnification. So, in subsequent discussions of optical instruments, we shall assume the image to be at infinity. Okay. So, before concluding, before moving on to the further discussions of telescope and all, let me just revise or summarize everything here. So, basically in this microscope we have three different portions in which the object was kept or at which the image was being formed. So, first was when the image is formed at the near point, as you can see, just let me iterate. So, it is that first image formed at the near point capital D. So, just let me write it here. So, first is image formed at near point capital D. Second is that image is formed at infinity. So, just let me check where it is written. So, second is that image is formed at infinity. This is for minus u and this is for so this is the image formed at infinity. Fine. So, next was for image formed at infinity. And third is when the image is formed at the when the object is at u. So, image formed when the object is at u. So, what is the complete conclusion? Conclusion is that you just need to find out the value of magnification. So, magnification for the image formed at near point is nothing but 1 plus capital D by f. Image formed when the object is at u, the magnification is nothing but equal to capital D by f. And when the image is formed at infinity, then the magnification nothing but equal to h by capital D. As you can see that the angle subtended equal to h by capital D here. So, these are the three relations which you need to remember for your complete concepts of microscope. So, first is when the image is formed at near point and the magnification is equal to 1 plus capital D by f. When the image is formed at infinity, then the magnification, please remember this is angular magnification. So, it is h capital small h by capital D, and similarly when the image is formed when the object is at u, then it is equal to capital D by f. So, 1 plus capital D, you just need to subtract 1 from it and you can find out the value of magnification at that portion also, it is capital D by f. Fine. Let us move on to the compound microscope concept now. So, what is this compound microscope? Let me just explain to you very clearly. So, a simple microscope has a limited maximum magnification which is less than or equal to 9. So, a simple microscope can only attain maximum to maximum portion of 9, greater than that is not applicable here. Okay, for realistic focal lengths. For much larger magnifications, one uses two lenses, one compounding the effect of the other, this is known as compound microscope. So, basically you just need to elaborate or magnify more. If you need to magnify more, if you need magnification of let us say 15, 20, 30, 100 and so on, then compound microscope has to be used in that sequence. So, these are nothing but usage of two lenses would have been used there. So, a schematic diagram of a compound microscope is shown in the figures as you can see. So, this is your eyepiece basically here, this is your bigger lens, this is your smaller lens. So, as you can see this is a focal length Fe, this is a focal length Fo, and then something is being made and the magnified image has been obtained here. Fine. Let us move on. What is happening? Let us see. So, first of all what is happening here is that the lens nearest to the object is called the objective, forms a real inverted magnified image of the object. So, the lens nearest to the object, is called as the objective. As you can see this is called as the objective, forms a real inverted magnified image of the object. As you can see this is a real image, this is an inverted image, this is an inverted image and this is a magnified image. As you can see this is a magnified image. Fine, quite evident, everything is clear till now. This serves as the object for the second lens, the eyepiece. So, this is basically called as eyepiece. As you can see from the subscripts also, O stands for objective, E stands for eyepiece. So, this serves as the object for the second lens, the eyepiece, which functions essentially like a simple microscope or magnifier, produces the final image which is enlarged and virtual. Quite evident, everything is very much explained clearly here. So, this serves as the object for the second lens, the eyepiece, which functions essentially like a simple microscope or magnifier. Basically, its work is to again just simply magnify. So, what you need to magnify now? You just need to magnify this image now here. Okay, produces the final image which is enlarged and virtual. So, as you can see, this has been enlarged and virtual being created in this portion here. Fine. The first inverted image is thus near the focal plane of the eyepiece. As you can see, this is near the focal plane of the eyepiece at a distance appropriate for the final image formation at infinity. So, somewhere at infinity the final image would have been formed. So, this is the final image being formed, or a little closer for image formation at the near point, or a little closer for the image formation at the near point. So, either the image would have been formed here or it would have been formed here. So, two different instances, as there were 3 instances in the previous portion, or 2 instances I have made in this compound microscope portion. Fine. Next is clearly the final image is inverted with respect to the original object. As you can see, this is the original object here and this is the final inverted magnified final magnified virtual image being formed. Okay. We now obtain the magnification due to a compound microscope. So, let us derive now for magnification due to a compound microscope. So, again simple mathematical formulation, nothing very typical in it. So, the ray diagram of the figure shows that the linear magnification due to the objective as in this objective lens will be nothing but namely h dash by h, which is equal to m naught, which is equal to h dash by h, which is equal to also equal to capital L by f naught. Fine. Where first of all, what is L here? So, as you can see, the L is the distance, nothing but a distance between the second focal point and of the objective and the first focal point of the object, that is FE and FO. So, basically it is the distance, this distance being talked about here. Okay. So, this is equal to capital L by f naught, where we have used the result tan beta is equal to h by f naught, which is equal to h dash by L. So, basically how was this being derived? So, from this mathematical calculations you can find out that tan beta is equal to h by f naught. As you can see, this is equal to h by f naught. So, basically you know for this triangle here. So, this is h, this height is h, this is f naught for you, hence this will be equal to h by f naught. And similarly for h dash by L you can do for the similar sequences here, that this is nothing but this complete length. So, you can do it for this triangle, which is equal to h dash by capital L. Hence, you can find out the value equal to h dash by h is equal to L by f naught, and hence this is being obtained here. Fine. Here h dash is the size of the first image, the object size being h and f naught being the focal length of the objective. Everything is same instance. So, the h dash is the image, h is the object height, and so on. The first image is formed near the focal point of the eyepiece. Quite evident, as you can see, the eyepiece is nothing but the name of the second lens. It is formed near the focal length of the eyepiece. What is distance L? Distance L is nothing but distance between the second focal point, of the objective and the first focal point of the eyepiece, which is Fe is called the tube length of the compound microscope. So, this is nothing but tube length. So, tube length has the name of L, hence the denotation is capital L here. As the first inverted image is near to the focal point of the eyepiece, we use the result from the discussion above for the simple microscope to obtain the angular magnification ME due to it, where when the final image is formed at a near point is ME is equal to 1 plus d by Fe. So, just angular magnification, when you find out for this portion here, you can find out that magnification tan theta is approximately equal to theta, which is equal to 1 plus capital D by Fe. So, capital when please remember, this is only when the final image is formed at the near point. When the final object is formed in infinity, then angular magnification will be due to eyepiece will be equal to capital D by Fe, and thus the total magnification when the image is formed in infinity is equal to m naught Me. So, basically three different formulations are to be used here. First of all, when we are trying to find out the initial magnification, and then we are finding out when the final image is formed at the near point. Hence, for near point we can find out equal to 1 plus d by Fe, E for eyepiece. Now, when the image was formed at infinity, then this is equal to capital D by Fe. And hence, because it is a summation of two different things, therefore, what we did is the complete magnification is, we in the previous sequences of combination of thin lens and content, we understood that magnification is nothing but the product of M1 M2. Hence, this will be product of again M naught Me. Therefore, this will be equal to nothing but L by F into D by Fe. Therefore, the total magnification when the image is formed at infinity is M is equal to M naught Me, which is equal to L by F naught into D by Fe. So, next thing is, so this thing has been explained, this thing has been explained. Now, clearly to achieve a large magnification of a small object, hence the name microscope, the objective and the eyepiece should have small focal lengths, quite evident. So, if these things are small, the magnification would increase very drastically. So, in practice it is difficult to make the focal length much smaller than 1 centimeters. Also, large lenses are required to make capital L large. So, for example, with an objective with FO, so let us say the FO for this portion is, let us say 1 centimeter, and the eyepiece with focal length of 2 centimeters. This is 2 centimeters, and a tube length of 20 centimeters. This tube length is given to you as 20 centimeters. The magnification is just putting the result. So, this is 220. This is your 1, capital D is 25, the image because the image is formed as near point, it is therefore 25 centimeters, and F is 2 centimeters. Just putting the values, you can get the answer equal to, so this is 250. Hence, the magnification 250 is obtained. You can see in the simple microscope only the magnification less than equal to 9 was being obtained. Here 250 times magnification can be obtained. So, this thing explained, this thing explained, this thing explained. Various other factors such as illumination of the object contribute to the quality and visibility of the image. In modern microscopes, multi-component lenses are used for both the objective and the eyepiece to improve image quality by minimizing various optical aberrations or defects in lenses. So, these are basically the what we can say applications. So, in modern microscopes, multi-component lenses are used for both the objective and the eyepiece. So, this is basically objective, this is basically eyepiece, to improve image quality by minimizing various optical aberrations or defects in lenses. Okay. So, that is a complete end of your microscope, I guess. In the next lecture, we will start with the telescope, then summary, and that will be the end of your ray optics and optical instruments. So, just a course progress. So, introduction is being done, reflection of light by spherical mirrors is done, refraction and total internal reflection is being done, reflection at spherical surfaces and by lenses is being done, and right now we are on the 5th point, that is optical instruments. So, after optical instruments there would be summary, and hence that will be the end of your complete lecture series of ray optics and optical instruments. So, for now, thank you so much.